All right, in this explainer, we are going to tackle a classic computer science problem, and you're going to see how picking just the right tool for the job, the right data structure, can transform a tricky challenge into a solution that is just surprisingly elegant and incredibly fast.
So here's our game plan. We'll kick things off by defining the problem. Then we'll look at a couple of common ways you might try to solve it. And we'll even expose a frequent trap that a lot of people fall into. After that, we get to the really good stuff, the optimal solution. And finally, we'll put it all side by side to see why it wins.
Okay, first things first. Let's really set the stage and make sure we're all on the same page about what we're trying to do here. This is one of those problems that really tests how you think about data and efficiency.
So, this is the question, and it comes up all the time in technical interviews. On the surface, it seems pretty simple, right? Just find the biggest number in a small chunk of an array. But the real challenge, the part that interviewers really care about, is how efficiently you can do it as that window keeps sliding along.
Just to visualize what's happening, imagine you've got this fixed-sized frame. That's our window. And it's just moving one step at a time, from the left side of a list of numbers all the way to the right. And for every single stop it makes, our one job is to shout out the biggest number that's currently inside that frame. So, where do you even start with something like this? Well, a pretty logical first thought is to just keep the numbers inside our window sorted. I mean, think about it. If your little collection of numbers is always sorted, finding the biggest one is a piece of cake, isn't it?
So you might reach for a tool like a multiset from C++. It's basically a container that, by its very nature, keeps everything inside it sorted at all times. This means finding the maximum value is super simple. You just look at the very last element. Done.
So how does this work in practice as our window slides? Well, it's kind of like a two-step dance. For every slide, a new number enters the window, so we add it. An old number leaves, so we remove it. And because the multiset handles all the sorting for us behind the scenes, both of those operations have a nice, predictable cost.
And what does that give us? Well, it lands us at a total time complexity of O of n log k. We do a log k operation for each of the n steps we take. You know, this works. It's a really solid first attempt, and it would definitely get you some points in an interview. But the big question is always, can we do better?
Okay, now let's explore another idea. One that seems even faster and more intuitive at first glance, but it's hiding a pretty common and sneaky trap.
Let's talk about the priority queue, or a max heap. This data structure seems like it was made for this problem. Its entire purpose in life is to tell you what the biggest element is, and to do it instantly, in constant O1 time. This sounds absolutely perfect, right? What could possibly go wrong?
Well, here's the trap. Getting the max value? Instantaneous. Fantastic. The problem comes when you have to remove the element that just slid out of the window from the left. See, a priority queue is designed to remove the biggest element, the one at the top. It's incredibly inefficient at finding and removing some other random element from the middle of its structure.
Now, you could try to be clever and use a workaround, like a lazy pop. The idea is you just don't remove the old elements right away. Instead, when you need the max, you peek at the top, check if it's still in your current window, and if it's not, you pop it off and look again. But this just adds a bunch of clunky logic, and worse, it can totally mess up our performance guarantees. So what we really need is a data structure that gives us that instant max and lets us efficiently handle removals as the window slides. And this brings us to the most elegant, optimal solution, the one that will really impress in an interview.
The answer is something called a monotonic deck. We'll use a deque, that's pronounced deck, like a deck of cards, which is just a queue where you can add and remove from both ends. But we're going to apply a special set of rules to it to keep it monotonic, which is just a fancy way of saying we're going to force it to stay sorted in decreasing order. If we can do that, the maximum element in our window will always be sitting right at the front.
The magic behind this is a simple three-step process you follow for every single number. First, clean the front. Get rid of any indexes at the front of the deque that are now outside our window. They're old news. Second, clean the back. Now, before we add our new element, we look at the back of the deque and kick out anybody who is smaller than our new element. This is the crucial step that keeps our deque sorted. And finally, third, add the new guy. We just add the index of our new element to the back. That's it. That's the whole algorithm.
And if you follow those three simple rules, the entire problem just melts away. Finding the maximum value is no longer a search or a complex operation. It's literally just taking a quick peek at whatever's at the front of our special deque. It's simple, it's blazing fast, and it is always correct.
All right, let's pull back and put all these methods we've talked about side by side. This is where you'll really see the light bulb go on and understand why that last solution is such a massive game changer.
This table really tells the whole story. You can start with a simple but very slow brute force approach. Then you get smarter with the multiset, which is a decent logarithmic solution. Then there's the priority queue, which is a clever idea with a fatal flaw. And then you have the monotonic deque. It is the only approach with a strictly linear O of n time complexity. And why is that? It's because every single number from our array gets pushed onto the deque once and popped off at most once. That's it.
And that right there is the big takeaway. The key to unlocking this optimal solution wasn't some crazy complicated algorithm. It was about thinking clearly about what the problem actually needed, fast max, efficient removals, and then picking the perfect data structure for that job. It's all about finding a smarter way to hold your data.